Okay, so the topic of my talk is Beyond Bias, Crafting the Fairness in Pythonic Machine Learning Systems. Before I delve deeper, just giving a brief bio about myself. I'm a machine learning engineer by profession and also researcher by passion. And I heavily work in machine learning algorithms, building fair and unbiased, all these kind of machine learning systems all around. So let's delve deeper into this. So the agenda of the talk firstly is going to be what is the machine learning, just to bring all of us on the same page. And then I'll talk about what exactly is the black box problem and why do we face it. And then how can we build fair and unbiased machine learning models. On top of it, we'll understand what is the machine learning test pyramid and how we can build some strategies around it. And if there are any technical debts, which I'm sure pretty much there are, while we are building such systems. And then towards the end, there is a conclusion and the two-liners from my side for all of you. Okay, so let's dig deeper into this. See, AI is kind of a very broad term, and machine learning is a subset of the AI in which you are just extracting or learning patterns from the data set, or you are explicitly programming, and then the data or the model in itself will understand what is exactly happening behind the hoods. And the deep learning is a subset of machine learning, which is extracting the patterns, and then it gives you certain output or real-time data-driven kind of a predictions. The example shown in here is spam email detection, which is an example of machine learning, and the handwriting recognition is an example of the deep learning. Now I have explained you the basics. Let me test the waters. I want you to take a minute and think. Think which of these faces are real. Please raise the hand if you think face A is a real one. Interesting. Please raise the hand if you think face B is a real one. Please raise the hand if you think face C is a real one. Thank you so much. Well, none of these faces are real. These people, they do not exist on the planet Earth, to say the least. I'm not sure about the Andromeda or other galaxies out there. But yes, these instances or the data patterns, these are generated by the deep neural networks. I'll explain what are the deep neural networks as we go delve deeper into this talk. But these instances or the faces that you can see in here, these people, they do not exist. So what is happening behind the hood is that the deep neural networks, they are understanding from the data set that you're providing, and then it is synthesizing or generating the new samples of the data, which look alike with the real data set that you're providing. So first understand what is the building blocks behind all these deep generative networks or deep neural networks. This is a basic architecture of the neural network. Given the data set as an input, you have the weights, sum, and biases, activation function. Just consider that the weights, biases, sum, and activation as a machine learning model or as a black box, and then it gives you an output. An output could be, let's say you are doing a image recognition or maybe just doing a sentiment analysis, then whatever the use case is, that's going to be your output. Okay, so let's understand this entire structure through an example. So this is my Fluffy, my pet dog. I'm just doing an image recognition on it. So given an image dataset as an input, the image will not be fed into the model, but it will be in a form of a pixels that the model is understanding. So you can see the pixel, the small part of it. And then you have the image classification algorithm. And then it gives you an accuracy or a confidence whether this image belongs to which animal category. And it clearly states that it's of 92% accuracy, it's a dog category animal this belongs to. Right, so this is how the image recognition working, and the framework or the basic framework that we saw in the previous slide is working behind the hoods. Now, if I want to deploy this image recognition in the production, so let's see how the entire end-to-end pipeline will look like. This is a very high level of the pipeline that given a data set in the build pillar, data set as an input, you are ingesting the data, and then you are training the model on that data. Then, of course, you are training and testing, and then once you are very much happy with what the model is providing you as an input, then you are just packaging that model. And further on, you are registering the model and jumping to the next state, which is the deployment stage. And then goes the monitoring stage. In the monitoring stage, you are monitoring how your model is performing over the period of time. And then you're circling back to the build stage over here. If, let's say the model has been deployed in production in 2023, now that model has to be auto-tuned. It has to ingest the new data set which is coming in so that it's not stale. So therefore, you go circle back to the build stage again. So this is how the entire pipeline of machine learning looks like. But wait a minute, what if something goes wrong, especially in the build stage? Let's see. Okay, so did you know that only 13% of machine learning models actually make it to the production and 87 of them never see the light of the day? Well, that was reported by the Venture Beast. Let's see. One of the very funniest example, and the core of my talk is a black box problem. I'm just giving you a couple of seconds so that you can see through the prompt or the responses being given by the chat GPT. And here I'm using the 3.5 version of the chat GPT, which I'm pretty much sure that everyone is aware about. So the prompt given over here is the doctor yelled at the nurse because he was late. And the response corresponding is, who was late, which is the question I asked. And you can clearly see that the doctor, or he's referenced to the doctor rather than a she, right? Similarly, in the next one, the doctor apologized to the nurse for her late arrival to the emergency room. So you can see the funny response being given by the chat GPT, which doesn't make sense, right? Okay. And the next example is, word embedding. So what happens in the word embedding is, it's also one of the core machine learning, or you can say a very core NLP algorithm, in which the words are represented in a vector space. You can see the man, women, these are different words representation. In this Cartesian plane, it's a word vector space. And you can see the closeness of the homemaker with the women. So this word-to-vec algorithm, which is being developed by the Google, it has been trained on a biased data set, which is a Google News data set. So we know that, right? If you're training the algorithm on a biased data set, the response is going to be biased. So this is also one of the core black box problem issue. Okay. So now we have seen, these are certain reasons why the black box problems are happening, or some of the examples. But what exactly is the reason or the rationale why machine learning model is giving you unfair responses or some biased outcomes for that matter? So the first important reason is when you have the biased training data set. When the model is trained on a skewed distribution of the data, then of course the response given by it is going to be biased. So that's one. And when there is a lack of diversity within the data set. Now someone asked me the other day, the world in itself is a bias, Rashmi. How can you train the model or force the algorithm to be not biased? And I'm pretty sure that's when she asked me this question and I was like wondering, well, I know this is what the reality is, but we need to make the models and more algorithms more, like equally proportionate. And when you have the inadequate evaluation metrics, that's also one of the reasons that why we have unfair responses. Systemic bias in the cognitive and the proxy biases, these are also different types of biases which are engulfed in our life so much so that we are not even aware about. I just give you an example. So Amazon has this hiring algorithm, which was scraped off like a couple of years ago. They were like discarding the applicants. So everyone was applying for the job interviews or, like for recruitment purposes and all of that. And the women applicants were being discarded frequently from that algorithm which was being used. So AI model was discarding every women applicant. So when the model in itself is being trained on a bias, some such kind of information, then of course the response or it can't be deployed. You have to scrape it, right? You can't deploy that kind of a model in the production environment. So those are like some of the reasons and the rationale that why model gives such responses. But what if we want to build, before than that, this is one of my favorite memes, and I'll just let you a couple of seconds to read through this. Okay, so this actually goes back to the garbage in, garbage out, right? You're putting in the garbage inside the model, then of course the responses are going to be the trash for that matter. And this is, so now let's build fair and unbiased models, and what are the reasons and how we can actually do it. So first, of course, we need to, thumb rule is collect the diverse and well-represented data set. That's the thumb rule and very important part of it. Next is you need to monitor for the different kind of biases which could be prevalent in the algorithms that you're training on. And the third is there are like certain pre-processing, post-processing techniques, like data augmentation techniques are there, feature selection techniques are there. You need to implement that. And the fourth one is the algorithmic fairness techniques. I'll show through an example, like a couple of these techniques, how we can actually ingest these techniques and make our model much more fairer and unbiased, of course. And last one is, second last one is explainability. You know, what explainability is, of course, it will be covered in subsequent slides, but just the high level view is how your model is interpretable, or how your model is giving the responses, which is human understandable, whether you are able to comprehend why the model is responding to a certain, output or input which is being fed into it. And the last is having the thorough end-to-end testing at every stage of your machine learning pipeline. It could be data ingestion pipeline, building, testing, modeling, every stage of this ML pipeline. Okay, so now let's see through an example how we can actually incorporate a couple of the techniques which we saw before. Okay. So first of all, I need to explain you what is the use case that I'm trying to deal with it. So given a German credit data set, what we are trying to achieve from that data set is a loan classification, right? You are given certain parameters, features around it in that data set. It's an open source data set. And you have to predict what is the probability a person will get the loan sanctioned versus not. So that's what our aim is. And there are certain protected attributes in the data set. What I meant by protective attributes is gender, race, ethnicity, age. These are certain protective attributes. So we need to train a model which should not make the biased responses based on these protected attributes. So that's what our goal is going to be. So let's see. So first of all, you're importing a lot of packages and libraries, whatnot. And then, of course, you see the data set which looks like this, and it has certain columns: existing checking, duration, credit history, and so on and so forth. Then you also see that, how the distribution of the data set looks like. That's one of the part of the hot vector encoding, or maybe like just want to binarize the output, which is the target variable. Then you, of course, you're doing the standardization and encoding some of the categorical values. So what I meant by encoding the categorical, so this data definitely has a lot of numeric and the categorical. We want it to be numeric, like the entire end-to-end, the data which should be fed in the model should be numeric. So once we have seen that, okay, the next is splitting the data set. But before that, I think I'll just explain. Here I'm just trying to understand which all the features which really weigh and play an important role in building the classifier kind of a model for this loan classification. Okay, so this is a technique which I wanted to highlight, a SMOT. So it's synthetic minority, kind of an oversampling and undersampling kind of a technique. And that's one of the data augmentation technique, which I was discussing before. Why we are using this technique is because you see the distribution in the data initially was from 240. If you see the instances of the 0 were 240 and 1 was 560. So that is our target variable which was there before. After applying this MOT technique, you can see the equal distribution, right? So you want the target variable to be equally distributed so that once the model has been trained, it is not going to be skewed towards one particular class versus another. So that's how we can apply this kind of a pre-processing technique, which is called as a SMOT. And once we have applied, of course, we can build now, modeling around it and can see that how the model is now responding. There are like different accuracy, precision, recall. These are the different evaluation metrics once we have applied. And this is one of very basic examples that I'm taking, that XGBoost classifier, which is giving you kind of an 80% accuracy. It's a small data set, 1,000 instances it has. So of course the accuracy is 80%, which is fair enough. We can optimize it using playing around with certain hyperparameters, but again, so far it's performing well. So that is how we can do and ingest the pre-processing pipeline, or just using pre-processing technique of a SMOT and doing the data augmentation, and can build a classifier around it. Okay. Oops. Okay, so next comes the part of the fairness, which is how actually can we incorporate the fairness while we are building ML algorithms, right? So there are different techniques around it. The first is demographic parity, which is when your data set has different demography, or maybe like instances in the data set which has people belonging to certain different regions. And you want to ensure that the model is not skewed or maybe like giving output which is biased towards one group versus another. So therefore, you can use this demographic parity. And demographic parity basically implies that you are doing the prediction of the model on the basis of which are similar to a certain demographic group. So that one group is not there is not a disparity between the two different demographic groups around it. And then there is a statistical parity difference. It's again calculating the probability distribution between the two different groups that you have created within the data itself. And the third is equal opportunity difference. Like just an example that the male and a female, whatever the income that you want to predict for them, it should not create a disparity between those two groups. So grouping is decided upon our own hypothesis, how we want to create a group. So, and then we can apply these algorithms on top of it. I'll give an example. Circling back to the previous example which I shown, I'll just show you how we can implement it. Okay, so it comes in the optimization part. Okay, so this is statistical parity difference. How I'm calculating the statistical parity is, the credit risk, which is one of the last column in the German credit risk data set. I'm creating the privileged grounds. Okay, so this privileged ground implies a privileged group and an unprivileged group. I'm defining by myself what is my hypothesis telling, whether the women beyond the age of this belongs to the privileged group or whether the male belongs to this particular age is an unprivileged group, something around it. So it depends on your own hypothesis where you want to test it on. And then I'm just calculating, what is the difference. And then, of course, this is how the statistical parity, like the core of the algorithm, is implemented. And you can see this difference is very small, right? The smaller the difference is, better the model is going to be. So this is how we can incorporate the statistical parity difference. There is another, which is the predictive parity metric. It's, again, you can see the difference between the male and the female. And also just checking what is the difference. It's very less. Like, the male accept for this is because loan classification for a male and a female, right? So that's how the groups have been created on the basis of the gender. And you can see that both of them, the difference between both of them is like really less. And that's what we are aiming for. And just ensuring that our model is not skewed towards one distribution versus the another, or one class versus the another. Okay, so yeah, these are the two things which I wanted to show. Next, let's come back to the slides. Okay, now the core and the other part of my talk which covers is why we actually need to test the machine learning systems. Can anyone would like to give an answer for this? Why should we test machine learning systems? What's the necessity of it? Any volunteer? There is no right and wrong answer. Yes, please.
So we can check if there's no bias.
Right.
Yeah, basically, like any other piece of software, to see if it works the way we want it to work.
Absolutely right. So you want to find, if there is any root cause of the problem which could possibly arise, and also ensure that our model is performing in the intended way that we really want it to be. So that's our rationale. And there are a bunch of test cases that we can build, or different testers we can build around. The first is, of course, the unit testing, which we normally do for any kind of a software that we are deploying or producing. Integration testing, model testing, these are different testings which comprise in the entire machine learning pipeline. The important part is the fairness and the ethical testing is also there, which is, you are evaluating whether a model is biased versus not, and also just checking each and every module of this entire pipeline, be it a data pre-processing stage, augmentation, ingestion, or modeling stage. I'll give you an example of this unit testing and the model testing so that we can better understand and comprehend what is. Okay, but before that, I need to explain what is the use case here I'm trying to work around. So sentiment analysis, I'm pretty sure people must be aware, but just to give and bring us all up on the same pages, I'm really grateful to everyone, or especially the people or the organizers of this PyCon Italia conference for giving me this opportunity. So that shows a positive sentiment, right? And I don't like the pineapple on the pizza. And one of my friends, she said, you should definitely try it. You are in Italy. I'm like, no. So that's a negative sentiment. So that's, given a sentence, you are just trying to define whether it's a positive and a negative sentiment. And also, like, just taking this opportunity, right, to thank my friends who's coming all the way from India with me and just cheering me up for this talk. So wanted to say that's a positive sentiment which is coming up. So that's how the sentiment classifier I really want to build. And once we have built this model, now it's time for us to test it and see. So I'm just defining a certain class, which is, given a sentence, you're just vectorizing that sentence, right? And then you're creating a training and the testing, like 80-20 kind of a rule. Like some part of the data will go for the training, some other part will go in the testing. And then you are doing this unit testing. Okay. So in this unit testing, what I'm trying to do is, I really enjoy this movie. The acting was, fantastic or something. So it's a positive sentiment. So when we run this, we see 1 over here implies that it's a positive, 0 is a negative. And the movie was terrible. I don't like it, and I wasted my money. So that's why it's a 0 around it. So we can write these assert kind of a statements and just check whether our model is actually performing the way it is intended to be. So that's a very small unit test kind of a package available in the Python that we can use for writing the test cases, just to see whether our model is performing as is intended. The others are, here you are trying to understand. So this test model kind of over here we want to write this classifier kind of a report, or maybe like we are calculating accuracy. We want to calculate precision, recall, F1 scores. These are model testing kind of a techniques when we have building the model around it. I just ran it like before. Maybe like I just run it again and just see. Okay, so here we can see the first important part is the model testing. You can see the accuracy because the data is very small, so accuracy is like coming up 100%, which in ideal case is not possible whenever you're deploying model, right? And then the 1 and 0 is first test case has passed, this second test case has also passed. So this is how you can write actually small unit test cases. A very basic or a toy example I've just given it here just to show that, how we can build the test cases around it. Okay, so next comes in, let's go back to our slides again. Okay, so I want to ask this question to all of you. Whom do you think should be responsible if for any kind of ramifications or any kind of errors which exist in the models or whenever the models are deployed in production? The options are data scientists, business leaders, regulatory bodies, or the end users and the customers or the consumers, Oh, yeah, sure. Right. But you need to provide the rational.
But I need to provide the rationale.
Yes.
Okay, then B, because they're the bad guys, and C, because we need somebody to keep the bad guys in check.
I love this answer. Anyone else who would like to give the answer?
That's all been said.
Right, okay. Well, the answer is none of them. Okay, I mean, in a sense that all the stakeholders, they need to work in together fashion. You can't pinpoint someone, especially not the data scientists like us. So whenever we are building or deploying these kind of systems, it needs to cohesively work together. Because every stakeholder needs to work in sync with each other and should be able to have open communication, kind of a constructive feedback in order to build before deploying the models in the production, right? And there is actually one famous, so the other day I was I checked on the Twitter, actually it happened yesterday. So on the Twitter, someone has posted, how can I stick the cheese on the pizza? And the response given by the AI was, add a glue to it. Okay, why the Google AI gave such kind of a responses? Because it was trained on this Reddit data set. And in the Reddit, one of the user has replied, okay, add the glue on your pizza, so then it will be sticking together. So you can see, right, how the model is responding once you are feeding it the trash of the data in it. So, okay. The next part is, and something which is important is, why we need the trustworthy systems or why we need the transparent systems. Of course, autonomous driving, healthcare, these are the two domains which I've highlighted, but there are multiple domains out there. The stakes are like really, really high. if there is any flaw or fatal could happen, right? So there needs to be a transparency. The users need to understand why the model is responding to way it has responded. And the users also need to be held accountable, whether it's a machine learning system or whether it's a company in itself which has built a bias kind of a data and has also like model which has been deployed. So because the stakes are super high, that's the rational or that's the reason we need to have transparent and trustworthy ML systems. Okay, so how can we actually build some of those? I think the repetition will come in when you have the high quality, right? The data set which you are feeding in. And also you're ingesting the explainable models. I'll give you an example how we can build explainable models. And then you need to monitor and test your models regularly. Use the regularization techniques. These are certain techniques to regularize your model. It should not overfit or underfit for that matter. And then, of course, having the communication with the stakeholders, multiple stakeholders it could be, having them in the development process and involving their, kind of a mind or intellect while you're building in this development process will really help in building the trustworthy systems. And always try to improvise or regularize whatever the model that you have built. Okay, so this is one of the favorite topics actually of mine. Why we actually need the explainability for that matter. We definitely want to ensure the accountability. We want to ensure there is an effective collaboration and more transparency while whatever the model that we are building. And we just want, it should be human comprehensible. Should be able to understand by the humans why the model is giving you certain results around it, right? So let's see that in action. Okay. So this is, okay, again, I'm just coming back with this example of the sentiment analysis. So let's say you have built a sentiment analysis classifier, right? And then you want to ensure that the model is giving the correct responses. So I'm using a Lime, one of the packages available in the Python. And you can see the text with highlighted words. I really love participating in this conference, PyCon Italia. Again, just thanking my organizers and taking this chance at the moment. And you can see the orange one over here shows the words which are actually contributing and emphasizing why it is positive. So you can clearly see that the positive sentiment is really high and the words which are corresponding to it. So it's human comprehensible, right? And that's what we need. We need the explainable systems. We need the systems which are human comprehensible or understandable. Okay, so again, going back. This is quite difficult whenever we are building machine learning models because there are always like technical debts which are present and prevalent in there. For example, you have the data debt, right? You could have the algorithmic or lack of monitoring or testing or documentation for that matter. Like every stage corresponds to a lot of, there is a very famous paper actually by the Google which says like the hidden technical debts while we are building models around it. So you can see that the engineers themselves are aware that there are limitations, but still that is being deployed. Of course, there is no model which is 100% ideal or accurate, but to an extent, can we mitigate all these technical debts around it? Can we really ensure it? So let's see, there are a couple of strategies that I'll discuss. But again, these are not exhaustive strategies, but some of the important ones which I feel from my years of experience. What are the challenges and mitigation strategies that we can use in order to ensure that we are actually eradicating the technical debts? So what are the actually ways we can do it? Of course, data is like the thumb rule, right? The data is in your oil or whatever, see that the process is. When you have the data, just ensure that there are no missing values around it, or just ensure that the label errors and how the distribution of the feature is looking like. And then examine the model performance using some of the robust evaluation metrics that you want to use. Precision recall is one such, or L1, RMSE scores. It depends upon which kind of a use case, whether it's a classification or a regression kind of a use case that you're building. And then try to just automate the testing processes to build a robust system around it and just to verify whatever the test cases that you have built around. And doing the code refactoring regularly just to ensure that the code or the piece of the code which might cause a bottleneck, it's refactored and again, just trying to optimize the ways around it. And then, of course, using the model explainability, because we want to ensure that these opaque black box models are well interpretable, or they can be easily be diagnosed. You can actually figure out what could be the potential reason why it is not responding to the way it should be. Then you can use like some of the open source tools are there, which are available as Lime and Sharp. So that's how it can help in building the robust techniques around it. In the last, just wanted to leave like a couple of words for all of you, is building the fair, accountable, trustworthy machine learning system is very crucial, because we want to ensure that the benefits of these systems are widely accessible and ingested by everyone or enjoyable. And then we want to ensure that our models are very much transparent and also like trustworthy, because we want to mitigate any kind of a biases or any kind of unfair outcomes that it's producing. And therefore, we need to build like the robust test cases around it and have the testing mechanism in place just to ensure that we build reliable and fair ML systems. As someone who loves writing a lot of poems, so these are my couple of words which I've written for all of you. From data's haze to the ethics place, in ML's maze, let's shine the fair rays. Inclusions is our mission, a colorful composition, erasing biases is our unwavering vision. Thank you so much.
So thanks a lot. And we have more time for some questions. We have a lot of questions. And okay. First one, don't you think models should be tested statistically and not with unit tests? Okay, and after all, they are not deterministic, but rather stochastic.
I think I totally agree. There are certain stochastic test cases which are possible. And of course, there are a lot of test cases out there. Deterministic is also prevalent. Again, depends upon which use case are we trying to deal with, right? If your use case, it highly depends upon if your use case is, let's say, image recognition or a classification, right? Then probably you wouldn't like to write like the unit test cases the way that I have written, right? Ensuring that whether it's giving the positive versus the negative. You want to write certain different kind of test cases altogether. So again, I think I just circle back to which use case are we trying to deal with.
Second question, can you come up with an objective general definition of bias? Or can you speak of bias only on a case-by-case basis?
Sure.
Sounds tricky.
Yeah, I mean, everyone's perception is different how they look in through the biases lens, but I think in generic is when the model is not, when it's not penalizing one group over the another. That's how I would feel like that's what the bias of the model is, and that's what we want to ensure we build the fair kind of models. Does that answer the question? Who's ever has asked within this room? Okay.
The question is my credit risk model biased if it approves loans with higher probability to applicants who are more wealthy and own collaterals?
Well, okay. So when you're saying that the people, those who are wealthy, and then you have built a credit kind of a German credit kind of a, or maybe like using whichever the data set kind of a system, credit risk system. Okay, so it does depend upon various factors. So you can't definitely say that people, those who are wealthy, they will be penalized, but ensuring that it's being equally distributed within different classes of the data. Let's say in the data set, if you have all the wealthy people, right? Or it has certain collateral values, which are certain values which are higher than a threshold value, which you have defining around. Then again, it depends on what modeling that you want to do, right? I think I can't give the concrete answer to it, but it all depends upon what hypothesis you are testing on, what exactly the metric you want to evaluate your model on, and just ensuring that your model is actually working the way it is being intended for. Yeah.
Okay, the other one is, to measure fairness between groups, you need to have a list of who belongs to sensitive groups.
Yes.
Which seems like a risk. How to mitigate this?
Sure. Well, I think the data, so GDPR is also one of the basic Well, in the data set, you really need to have some sensitive features. But there are also like certain techniques which are fairness through unawareness. What happens in the fairness through unawareness is you are not making sure, your model is not aware what are sensitive features, but then you are building a model on top of it and ensuring that the model is fair. So that's called as fairness through unawareness, that the model is not aware about which are the protective or the sensitive attributes given in the data set. And you are building a model on top of it. And then, of course, you're tweaking some hyperparameters, optimizing on top of it. So that's also one such domain, which is a different domain to what I've explained here.
Another question. We should ensure the model having the same performance metrics among all classes of a variable. Just example, age. How you ensure fairness for minority classes?
That's what I've explained. I think the SMART and all these undersampling and oversampling techniques are there. You need to ensure that there is a well representation of the minority class in the data set itself. You can't have a skewed distribution that there is a majority, because the model is going to be skewed, right? It's if there is a less minority samples in the data set. So having the equal distribution of that data set is important. Yeah.
One.
Yeah.
If a variable is discriminative, wouldn't it be better to remove it? To remove if we assume it has no bearing on the probability of success. Can say, I don't know if I. Do you want to read?
Yeah, I want to
because
read that question.
It's not totally clear. I mean.
If variable is discriminative, wouldn't it be better to remove if we assume it has no bearing on the probability of success? Okay, first of all, I didn't understand what a discriminative variable is implying over here. Is there anyone?
Can you describe better the question? No?
I mean, if it discriminates from a group perspective, we assume it would inform the model in a way that is not, we do not perceive. For example, if you assume gender has no bearing on anything, why characterize data points based on gender? Just remove variable. Just measure everything else.
Oh, so you are saying if we remove just the gender variable.
If you assume gender that there's a bias in the distribution, just remove that. And
Okay, so if you want to remove one of the columns in the data set in itself, which is the gender, and you are saying that because of the gender it could be possible that it could lead some biased results, then what's the point of building a model around it, right? You're removing the entire one information. Okay, so I've explained also like the feature importance in the entire context. There are certain data variables which are cohesively correlated with each other, right? Before removing any column or before removing any kind of information which could help in modeling, I think then there is no point in building a robust model around it. So I personally don't think we can't remove a certain information from the entire context, because the model needs to understand the entire context and whatever the information is being provided to it in order to make a justified data-driven decision around it. And then on top of it, tweaking or doing some hyperparameter or whatever the optimization we want to apply, and then trying to understand why the model is performing the way it is performing. Yeah.
We have a second part of a previous question, that is how you ensure fairness for rare classes from a statistical perspective.
So how we can ensure the fairness through?
How you ensure fairness for rare classes from statistical perspective, and I think it's the second part of this one, I think.
Oh.
So I don't know where is the first part of the question.
Okay, so if there are, let's say,
the first question.
we should ensure that the model having the same performance
this
metrics.
is the second part, I mean.
Okay, if there are certain rare instances within the data set, then of course we can remove those instances, right? But I think the rare classes is something very high level or not very concrete kind of an example being provided in here. But if there are certain instances within the data which are null or doesn't make any sense within the entire analysis or during the EDA process, which is exploratory data analysis, then of course we can remove those instances all around. Yeah.
Thanks again.
No problem.